Subratno and the organizer for inviting me to this nice conference and giving me opportunity to speak here. So I will speak on existence of periodic bundle on certain surface of general type. So this is a joint work with Subratno. So before saying what is Woolridge bundle, so I want to say a few words of why Woolridge bundle, why this bundle is important to study. So this study of Woolridge module arises in commutative algebra context is long back. So it next is appeared in algebraic geometry context in late 80s. So the main question was the following. So suppose X is a hypersurface in a projective space Pn. So this is, since it is a hypersurface, it can be written as a homogeneous polynomial. So the question is, can this homogeneous polynomial be written as a determinant of linear forms? So written as a determinant of a square matrix with linear form, with entries or linear form. So this was the question. So for example, let us have a very trivial example. So if you consider the embedding of P1 in P2 by xy equals to y square, then this hypersurface is given by this new coordinate. It is y2 y1 square minus y0 y1. So this is P1 is defined by this. So 0 surface. Then if one can easily see that this equation can be written as a determinant of a square matrix, so entries are linear form. So now we want to extend this problem, just not asking only hypersurface in Pn. So we consider any subvariety. So we just consider any subvariety in Pn. Thus the dimension of X is equal to K. I always assume X to be irreducible subvariety. So now question is, then here when this K is not a hypersurface, then there is no meaning of there is no single equation. It is to define X, we need several equations. So for that, then what is the appropriate notion of this single equation? So we want to define a new form that is called Chow form. So what is that? So consider the Grassmannian of so Grassmannian. This is a Grassmannian of 4-dimensional K plus 1 planes. K plus 1 planes in Pn. So then consider consider a subset Z contained in ZR K to be the this is set of all points planes in GRK which intersects X. So we start with a arbitrary variety of dimension K, and this is the Grassmannian of all K 4-dimensional K plus 1 planes, and then consider all those 4-dimensional K plus 1 planes which intersects. So this is a divisor. So this is a divisor. So Z is a divisor in the Grassmannian. So therefore, it can be defined by one equation. So if we consider the Fluker embedding of the GRK, then consider the Fluker coordinates. And then the question is again, so can we write down these equations of Z by determinant of linear forms in the Fluker coordinates? So that is a question, and this so given any x, we can always associate a form. So that suppose if we say that f is the associated form corresponding to Z. Z, then f is called Chow form. So there are another way to describe this. So if we consider this incident relation, f is the set of all p and lambda belongs to Pn cross the Grassmannian, such that P belongs to. Then we have a two projection map from this, the Grassmannian, Pn. Then this divisor Z can be written as that is, we just take the inverse image. So P1, P1 inverse X, and then take the image. So now, so this is corresponding to any variety. Now, suppose we have a sheaf on Pn who supports the X. Let be a sheaf. So I'll assume order as torsion free sheaf. Torsion free sheaf whose support is X. Then we can consider the sheaf, the following sheaf, that is P1 upper star F, and then push forward into lower star. So this is a sheaf. This is a sheaf in the Grassmannian. So then the support of this is again a divisor in the Grassmannian. So we say that the form of the Chow form of it is the form associated to the codimension one part of the support of it. Now, given any torsion free sheaf, we can always associate a module, that is let M be the module which is the direct sum of global sections FD. So this is a module Now suppose if suppose there exists a locally free resolution. This is a S module where S is the polynomial ring, homogeneous polynomial ring of Pn. So this is a S module, and suppose there exists a locally free resolution. F n minus k F0 n. So such that the resolution is linear. So suppose there is a linear resolution, locally free linear resolution. So what does it mean? That means these are all free modules, free S modules, and everything Fi is generated by the module Fi is generated by degree I elements. So if this is the case, then basically there one can see that if I basically is isomorphic to some S cross Pi, where Pi is a finite dimensional vector space. Finite dimensional vector space concentrated on degree I. In degree I. So if this is the case, then this I'll just say this is pi 1. Let's call this number to be C. So this is the case, then this map is Pi induce a map from Pi to let me say what is W. Pi minus 1. Here W is that maybe I should have started with the projective space. I just here make this notation. When I write Pn, it means that P of W, where W is n plus 1 dimensional vector space. So then these maps, each I for each I, Pi we map induce a map from Pi to W cross Pi minus 1. And then again we have a map from here to W cross W tensor Pi minus 2. And since this is a complex, so this composition is 0. So therefore the image always contained in it induces a map from Pi to lambda 2 W tensor Pi minus 2. So in general, so if we take this, all this composition, then ultimately what we'll get, PC will induce a map from PC to W over C tensor P naught. So if we consider this W wedge product C, this to be the linear forms on the Grassmannian, then this induces a map to, I just call it PC tilde, to O minus 1, the Grassmannian GR, tensor PC to Grassmannian tensor P naught. So this is the vector bundle morphism. Then the theorem says that there is a theorem due to Heisenberg. Eisenberg says that if this is the case, then the chow form of F, the shape we have started with F, is given by just chow form. F is given by the determinant of this. Determinant of this integral. Here, the rank of P, C, and P naught are same, and so this will give a square matrix. This will define a square matrix, and the determinant is the chow form of it. So the question we are asking for that answers if we have a locally free resolution, linear locally free resolution of this model. So this is the question, and this is the answer. So if the question is now that finding whether M has a locally free resolution, linear locally free resolution of this type. So then the next theorem says that, so that is actually our motivation to define fully bundle in the way it is defined. So this proposition says the following. So let F be a coherent sheaf of dimension. When I say dimension of F means dimension of its supports. Dimension K in Pn with K is bigger than 0. Then the following are equivalent. So number 1 is that ith cohomology to state point I is equal to 0 for all I greater than 0, and the second one is hi f minus I minus 1. This is equal to 0 for all I less than k. And second one is that the module M which is I have already defined to be the direct sum of these global sections. Is Cohen-Macaulay. And M admits the S-free linear resolution. Minus K so this is a theorem which proved by Eisenberg. So this is so from this theorem, as I said that these two are equivalent. So we'll define a bundle to be Ulrich if it satisfies either one of these conditions satisfied. Or generally, actually, that in literature this is the definition for Ulrich bundle. So we define the definition now. So a torsion precinct, we'll say here on the torsion precinct, F is said to be Ulrich if hi f minus I is equal to 0 for all I greater than 0, and hi f minus I minus 1. This is equal to 0 for all I is less than. That K is the dimension of the C. So if if we define a Ulrich sieve like this, then from this theorem, it means that the Ulrich band this module admits a linear locally free resonance. So if once we have this, then we can write down the corresponding Chow form as a determinant of linear forms. So that is the motivation to defining Ulrich bundle. So then the question is, given a variety X which is embedded in some Pn with, say, when I said Ulrich bundle, then we have twisted by I think O1. So I think that here I have to mention. So here is Ulrich with respect to X. And this twisted means OX minus I, tensor equals. So when I say something Ulrich, then we have to specify which under which with respect to which line bundle this is this satisfies this condition. So the question is now, X is any variety in Pn, say polarized variety, so that means it's embedded by OX1. Then the question is whether the corresponding Chow form can be written as a determinant of linear form. It's the same as that whether there exists a Ulrich bundle on X. So this is the question, and then so the question, first question again asked by Eisenberg and Newton. So they asked that, so does the given a smooth projective variety polarized variety, does there exist a Ulrich bundle? So this is the first question. And then if the answer is yes, then what is the minimum rank? So if yes, then what is the minimum rank Ulrich bundle? So these are the two questions. So for when X is a curve, smooth curve, then it is easy. Then actually one can find out that there exists a unique line bundle for that. And then for higher dimension, people studied this problem, but there is no general result which says something about existence. But some particular kind of variety people studied. So higher dimension very rare has been studied, but only for surface people have studied. Many people have studied, and so far the known results are, according to my knowledge, is that so when X has quadratic dimension less than or equal to 1, then there are some result. Not for all surfaces, but certain class of surfaces it is known. So people have studied Bovil, Casanati, they have studied, and I think you guys also, Formo also have studied this for double plane. So if X if quadratic dimension of X is less than or equal to 1, then some result known, then some class of surfaces with quadratic dimension X is known. is known. The only bundle exists and it has rank 2. So then, which
minimum line bundle does not exist.
Most of the case line bundle doesn't exist. The line bundle is very rare. So now, then next question is when quadratic is equal to 2, means surface of general type. Then what can you say about that? So this is the question we have started working on, and what we have proved is that following. Our theorem is this. So if X is a surface with very ample canonical, very ample kx, that is that, and picard of X is generated by this. Is generated by kx. And one mild hypothesis we had that Q, this is my definition H1 of OX, Algebraic, is less than or equal to pi minus 1. Pi of X. So if this happens, then X admits a rank 2 liquid. So this is the theorem. So next half an hour, I will just give a brief idea how to prove this theorem. So clearly such a surface is of general type because it is quadratic dimension will be 2. And in fact, if canonical bundle is not very ample, then also our method will work. If we consider that, so it's ample, then it's very ample means that X for some M is very ample. So try to embed that X with that very ample. Then same argument one can work, one can use to prove this existence. So the main theorem which we'll use to prove this the following. So on that, I just say that let X be a smooth projective variety. Not variety, surface with Picard rank of X is 1. Then a rank 2 vector bundle is only if and only if E is initialized so that is E minus H naught of E minus 1 is equal to 0. When I say E minus 1 means X is a polarized, let's say OX. It's a polarized projective surface. Number 2, C1 of E is equal to 3 H square, where H is the hyperplane bundle, plus Kx. This is equal to X1. And C2 is equal to centimeters 5h square plus 3kx to h by 2 plus 2 into pi of x. So these are all conditions which are class and only the initialized property this one. So if this one can produce a vector bundle with these three properties, then that will give us a only bundle by this theorem. So our main goal is to construct a vector bundle which satisfies all this property. So so this is a theorem. So I will not prove it. I will not give a proof of this. It's not very difficult also. So one can prove that with all these conditions, those cohomology vanishes. So, so our goal is to construct a bundle which satisfies all this property. So how to do? So main there are three steps. So one is that. So it is known that it's a serial correspondence that is an extension to M. So E is a non-trivial extension. E is locally free. Summarize it. Where L and M are line bundles and Z is a zero-dimensional substring locally complete intersection. Then A is locally free, E is locally free. If and only if Z satisfies Calibrator property. Calibrator property for then dual tensor N. So K of X. This is the case for surface. So what is Calibrator property? Let me see. So we say that a zero-dimensional substring Z in X is satisfied, is said to satisfy CB for some line bundle if Z prime for any co-length one substring.
With every E or there exists Calibrator property, the open subset or any extension is.
Yeah, any extension with this type such that Z satisfies Calibrator property, then it is non-trivial extension.
Any E not equal to 0. Any is non-zero E.
Yes.
No.
No.
Extension is locally
So in that extension space, any point.
Yes.
That's what I.
So this is said to satisfy Calibrator property for L if for any co-length one substring. Z prime containing Z is not of L tensor IZ prime is equal to. So that means any section which vanishes on Z prime, then that section vanishes on J also. So this is the Calibrator property. So if that locally complete intersection which is a zero-dimensional substring which satisfies this property for this line bundle, then we say that Z satisfies Calibrator property for this, and in that case there is any non-trivial extension is locally free. So the first step is to find out a subscheme which satisfies Calibrator property for. So for our case, so in our case, we have assumed that it is generated by Kx and Kx is very ample. So we just embed X in Pn by Kx. So Ox1 is equal to Kx. So we have to construct a vector bundle with C1 is equal to from this 4h square. and C2 is equal to, so this is 4h square plus 2. So this is first one, and then second one. So this is first goal. First one is to construct step 1 to construct a
4h square, 3h square.
4h square.
C2 is
5h square plus 3
5.
to construct a vector bundle with this C1 and C2. And then to say something is initialized, the first condition, for that what we will do, we'll prove that, okay, so let me say, so the construction, what we'll do for this first step, step A1, is that to construct it, so step 1 is to construct a zero-dimensional subscheme. Subscheme of length 4h square plus 2 pi, which satisfies Calibrator property. Satisfies Calibrator property CB is OX pi. So what we can get is that if we take the extension, non-trivial extension of the form IZ4, this OX4 tensor ideal so ideal C of Z, but the Z of length of Z is so by this fact, this A is a locally free because Z satisfies Calibrator property for this is trivial, so L12 is O and M is O4 and K is 1. Then this is a locally free, so we'll get a vector bundle with C1 is 4h square, 4h, and C2 is of course one can easily calculate that this is the C2 because the C2 of this E is the length of Z. So once we do this, then this two conditions will be satisfied. So we get a vector bundle which satisfies these two conditions.
Is it stable or
No, that I'm coming. Okay. So this is the first. Now we need to prove that that E satisfies this. It's initialized. Age naught of E minus 1 is 0. So for that, the next step is step 2. What we do, we prove that a general element in this extension is stable. Okay. So the step 2 is that a general element in this extension is stable. So if we take a vector bundle like this, then if we tensor by O minus 1, then E minus 1 will have C1 is 2h and C2 will be 2h square plus 2 pi. So next is so once we prove this, that's general element stable. So if we just twist it by O minus 1, then this is again stable. So then we consider the modular space M rank 2 stable vector bundles 2h and h square plus 2 pi. I think that is it. So this is exactly if we just twist this E by O minus 1, then the C1 and C2 will have this. C1 will be 2h and C2 will be this. So then from this construction, we can say that this modular space is non-empty. And then what we prove that a general element of this modular space doesn't admit any section. Okay, so step 3, a general element E, say F equals to N root 2H V square plus 2 chi doesn't have any sense. So you take a stable bundle with this property, which doesn't have a section, and then twist by O minus O1. Then what we get? That E will have all the property which we wanted, all the three property. So that will give us a holding bundle. So the main hard part of this construction is that to construct a zero dimensional subscheme which satisfy Calibrator property of this length. So that is the hardest part, and our idea is just sketch roughly. I sketch this how this construction goes. So one fact we will use, the fact is following. Suppose X is a smooth positive surface with picard of X is Z, and C is a smooth curve in the linear system of XM, and F is any morphism, non-constant morphism from C to some PR. Then a general member in the linear series F upper star O1, OPR1. This is a line bundle on C. So take a general section. So its divisor is a reduced divisor. Satisfies Calibrator property. So Calibrator property for OM tensor KX. Yes. So this is the fact we will use. So what we need to do to say our result, that so we want to say this if we take m is equal to 4. So in our case, if we take m is equal to 4, and we know that kc is equal to 1, can easily put. Sorry.
When you say fact, it is easy to see or it is somebody's result?
This fact, this is not easy to see.
No, when you say
This-
fact, I am confused.
Okay, so when I say fact means is some theory, we are not going to
Somebody's here.
somebody's theory. Okay, so using this, basically what we need to do, basically we need to produce, so it is enough to, so it is enough to produce a curve C in OX4, this linear system, smooth curve, and a line bundle L of degree is 4h square plus 2 pi, which is base point free. So if we produce a smooth curve in this linear series and a line bundle of the degree this, which is base point free and admits at least two sections. So then this line bundle will give a map from PR. And this line bundle has this degree is this. That means if we take a general element in this linear system, that will have degree 4h square plus 2 chi. So length is 4h square plus 2 chi. And by this theorem, that gamma, if we take this, then if we take gamma to be this linear system in star O1. So then this will have length of gamma will be by construction 4h square plus 2 chi. This one, because since we have assumed in this construction, if you put there is base point, then we get this map. So using this theorem, we'll get a subscheme 4h square plus 2 chi, which satisfies Calibrator property for O5 by this theorem. So now the whole thing is to construct a curve and this a line bundle of degree this, which is base point free and has at least 2 sections. So for what do we do for that? So there are several difficulties in this proof, in this construction. So number one is that first construct a line bundle of this degree, and then once you get that a line bundle, then the next step is to prove that it has at least 2 sections. And the most difficult part is that it is base point free, to prove that it is base point free. So what we do, what is the construction is the following. So we just choose a C0 be a very smooth curve, be a smooth curve. In OX. So we take a smooth curve and then we just consider this line bundle. That is the line bundle. OX4, yes.
In this case, you do not need the map is given by the complete linear system. Any linear system is sufficient.
Yes.
Any linear. But base quantity, I mean.
But any linear system will not give you this. This will be changed. If you take any linear sublinear series subsystem, it's not complete, then you will not get that appropriate divisor there. If it is not complete, then you will get something here sub of this. Right? That is not complete. So you cannot write down what is the divisor, what is the degree of the divisor. Those things very difficult to complete.
Even by the
Complete system. Okay, so first we consider this line bundle OX4 and then restrict on this curve C0. So this is a line bundle. It's a line bundle on C0. Okay. Then first our construction is choose Z1 to be the general hyperplane section, H1 intersection C0, say general hyperplane section. Section with respect to that line bundle OX4 restricted to C. So here is just not just arbitrary general hyperplane section. That hyperplane section should be general with respect to this line bundle. This is very crucial assumption. And Z2, once we got this Z1, and then how do we construct Z2? We just consider this Z2 to be again a general hyperplane section. With respect to the line bundle OX4 tensor O C0 minus Z prime, which is contained in C0 for all Z prime contained in Z1. So take any subscheme of Z1. Then you just twist to that line bundle OX4 restricted C0, and then twist with by this ideal sink. So then with respect to these line bundles, you construct a hyperplane section. Then Z is now my Z1 union Z. So I got a subscheme of length 4h squared. Contained in Z1. Take any subscheme of Z1. No restriction. So there are finally many subschemes, right? Because Z1 is finite. So there are finally many line. This way you will get finally many line bundles. Okay, so for each, with respect to each line bundle, this should be general, this intersection. Okay, so if you fix a line bundle, fix a Z prime, and then choose a open subset with this property, and then they change the line bundle called take all the successive open subsets and intersect that. That is again open subset. So you can always find out the general hyperplane section with this property. So now Z to be Z1 union Z2. So now it's obvious that this is coming from O2. C0 is O2 and this is a hyperplane section. So the intersection number is 2h squared. Similarly, this is also 2h squared. So total length, so coordinate of Z is 4h squared. So something magic happens here. So which actually we need that is Zi imposes exactly 2h squared minus 1 independent conditions on the sections of O4. So these are all easy to see using some cohomology computation that Z1 imposes 2h squared minus 1. So Zi is straight on sections of OX. And this Z, this together imposes at least 4h squared minus some number independent conditions on OX. So this number is always this number is bigger than equal to this number is bigger than equal to 4h squared minus 2pi. This number is bigger than equal to this. Then what is our idea? Idea is that from this Z, choose a 4h squared minus 2 chi points such that imposes independent conditions on X4. And then, so next step is that step 1 is that choose 4h squared minus 2 chi points from Z, which imposes independent conditions. Since, as I said, this imposes at least this many independent conditions, which is bigger than this, so always you can find this many points. Conditions on OX. And with the extra property such that Z intersection Zi, this length is at most 2h squared minus 2. So this, as I said, this is the magic happened here. As I said that Z itself imposes exactly 2h squared minus 1 point, independent conditions. So this, and we want 2h squared minus 2 points from that which impose the independent conditions. So that always you can find. So the next is that step 2, what we show that if any p from Z minus Z is, I just call this Z prime or Z tilde, Z minus Z tilde, then what we can show that this Z tilde union P always imposes for any P independent conditions on. And this is the important part because we want to prove that if we take this, this will use to prove that the line bundle we are looking for, that is base point P. So there, this will be used. So to construct two sections such that the intersection is empty. So that is the idea. So I think I don't have much time. So this is these are our main steps, and of course there are few things I need to explain to why that. What is the line bundle? And so the line bundle is basically, we just take OC to tensor O minus Z. So just now take a smooth curve which is contained in. So now choose a smooth curve. Smooth curve in OX4 C containing Z. Containing Z tilde. And then you just take this line bundle O4, O2, C restricted tensor O minus Z tilde. So this is the line bundle which has exact degree, because this is 8h square and this is 4h square minus 2 pi. So this degree will be exactly 4h square plus 2 pi. And because Z tilde has this property, one can easily show that this line bundle is base point free, and it is it has at least two sections. So that will give us the line bundle and curve, and so we got a vector bundle. And then the second step to say that a general limit is stable, that is very easy and elementary. Just we have to count the dimension of the extensions. Okay.
Thank you. Is there any question? If there is no more question, let's end the speaker. So we will meet at 3:50.
Hello, is the webinar host there? Hello. I hear you very weakly. Yes.
Oh, can you hear me now?
It's better. Yes. Can you give me the right to share a screen so that I can put my file?
Yeah, you can share your screen.
Excuse me?
Yeah, can you share your screen now?
Okay, very good. No, it says that host disabled part.
Okay,
No.
I will get the ID. Whatever.
Yeah. Hello?
Yeah, please wait. I'll
Sure.
get it done.
Given permission.
Can you try again?
Yes, I'll try. Okay, very good. Yes. Let me just do this. Share. And then this.
Yeah, we can see this.
Let me just do something. Presentation. Yeah, is that okay? Do you see that?
Yeah, this is fine.
Let me start video. Yeah. Do you see me also?
Yeah, we can see.
Okay, very good. So I await your orders to start, when you tell me.
Yeah, we will start at 3:50, 5 minutes.
Okay, good. Excellent.
No, this is the last.
Sir, can you hear me?
Yes, I can hear you.
We'll start a little late. We are running.
So you are saying I can start?
No, we'll start after a minute.
I hear you very badly. So perhaps you can repeat what you said.
We'll start after a minute. We're running a bit late.
So you are saying I can start?
Now we can use mic.
Okay. Sorry for that. We'll start after a minute or so. We are running a bit late.
Okay. So we are waiting how long?
For a minute or couple of minutes.
Okay, very good.
Hello, Oscar.
Hello.
This is Suratno.
Hello, Suratno. I recognize you.
So maybe I'm having tea within 2-3 minutes.
You want to wait for 3 minutes? No? Sorry?
Yeah. 3 minutes, maybe.
Okay, you let me know.
So we are going to start now.
Very good.
We are pleased to have Professor Oscar Garcia Prada from ICMAT. He will speak on Higgs bundle and higher Teichmuller spaces. Over to you.
Okay, thank you very much. Please complain if you don't hear me well. So I want to thank the organizers and especially Suratno for the kind invitation, and I'm very sorry that I cannot be there. My last trip before the COVID pandemic was to India, actually, just by the end of February and 2020. So, and I'm really sorry that the problem that we had yesterday with the internet in my institution that has been victim of a cyber attack, and all the connections, internet and so on, have been cut indefinitely. We don't know when we can be restarting. Anyway, let's get to the subject of my talk. And so I will consider S to be an oriented, a smooth, compact surface of genus bigger than 1. And we have the fundamental group of S. And then we consider GR to be a real form of a complex semisimple Lie group. This means GR is the fixed point of fixed points of group for an anti-holomorphic involution of G. So if you have SLN for example, then a real form is SUN or SUPQ and so on. Also, sometimes, in fact, this covers also the fact when GR itself can be complex, because every complex semisimple group can be realized as a real form of the double. So we can consider an involution, an anti-holomorphic involution in GR cross GR, a natural one, where GR appears as the fixed points. And we could do also reductive groups, but today we are concentrated on semisimple Lie groups. Okay, so we want to study representations of the fundamental group of S in GR. And the representation is simply a homomorphism from the fundamental group to our group. And in order to have a nice set of equivalence classes of representations, we want the representation to be reductive. That is, that if we compose the representation rho, this one here, with the adjoint representation, that the composition decomposes as a sum of irreducible representations. And so I will denote by this plus the set of reductive representations, and then the set of equivalence classes by just conjugation of an element in GR is actually is what we refer as the moduli space of representations of pi 1 of S in GR, or simply the GR character variety of S. We will use the two ways of thinking. So is this a space? And this space is endowed with a structure of an analytic variety. And if GR is algebraic, it's an algebraic variety. Okay, so we can associate topological invariant to a representation. And one way to do this is recalling the fact that representations of the fundamental group equivalence classes are actually in correspondence with isomorphism classes of flat GR bundles on the surface, right? And so this is simply the representation is a holonomy of the flat representation of the flat bundle. And so assuming that GR is connected, and well, we will see in the talk some disconnected groups, but most of the time GR will be connected. So GR flat bundles are on a surface are topologically classified by elements in the second cohomology group of S with values in pi 1 of GR. And this is isomorphic to the fundamental group of GR, which in turn, because HR, oh, sorry, I haven't introduced with what is HR. HR here is a maximal compact. I will come back to that. So HR is the maximal compact of GR. So GR retracts into HR. So the fundamental group of GR is the fundamental group of HR. So I have been going ahead of my own notation later. Okay, so topological invariant is this element in the fundamental group of GR. And then we can define the subvariety of representations in the character variety, whose topological invariant is a fixed value C, right? This element C in the fundamental group of GR. And so a very well-known fact is that if GR is compact, like for example, SUN, you know, or is complex like SLNC, then the group of connected components here is actually isomorphic to the fundamental group of GR. So the fundamental group of GR classifies connected components of the character variety. Yeah, this happens if the group is compact or complex, right? And so then the situation is very different for non-complex and non-compact real Lie groups. And in fact, the map that associates to to the given component, this continuous map, a given component to this element in the fundamental group of GR is generally, in this situation, non-complex and non-compact, is neither injective nor surjective. Now, to illustrate this fact, let me consider the simplest case. This is the case of the group SL2R. So SL2R is a real form of SL2C, right? Given by the conjugation that to a matrix A, you associate the conjugate of this matrix. And so in this situation, the topological invariant is, because the fundamental group of SL2R, the maximal compact of SL2R is a circle. So the fundamental group is given by the integers. And so you can associate to a representation an integer. And in this context, it's called the Euler number. And so then you can consider the subvariety RD of representations of the fundamental group in SL2R, fixing the Euler number to be D, right? So a very old result by Milner tells us that actually, unless the degree, this Euler number is bounded in absolute value by the genus of the Riemann surface, of the surface -1, then this is empty. Yeah, so this violates the surjectivity. So not every value of the topological invariant can occur here, okay? And, but moreover, several years later, like 30 years later, Goldman and Hitching, using different methods, prove that in fact this RD is connected if the Euler number is in absolute value smaller than the G-1. So the Milner inequality is strict. And they showed that in fact RD has 2 to the 2G connected components if the Euler number is actually in absolute value is G-1. So this violates also the injectivity, right? So you can see in SL2R this phenomena, but more relevant, or very relevant to, equally relevant to this talk, is the fact that this, that we will call R max, maximal Euler class, either positive or negative, that has 2 to the 2G connected components. Each connected component consists entirely of Fuchsian representations. These are discrete and faithful representations. And so this, via the uniformization theorem, Riemann, Poincaré, etc., this can be identified with the Teichmüller space of the surface that parameterizes complex structures on the given, I will assume the surface to be smooth. Yes, so this was observed by Goldman in his thesis, actually, right? Okay, so the question that I want to address in this talk is whether there are other simple groups, simple Lie groups, with similar features to those of SL2R. What do I mean by this? To be precise, we are interested in simple groups for which the moduli space has connected components not distinguished by the primary topological invariant. The primary topological invariant is the invariant topological invariant that I defined above, is the element in the fundamental group of the group, like the Euler thing here. And components that consist entirely of discrete and faithful representations. Yeah, this almost by definition we can say, at least, or a first attempt to a definition is what we will call higher Teichmüller spaces. So over the years, 2 classes of groups have been identified initially. The first class is the split real groups. Split real groups, these are, you know, like for SL and C, SL and R, right? This is real form. And another class is the non-compact Hermitian groups of tube type. I will discuss this. These are groups for which so what we call Hermitian groups are those for which the symmetric space defined by the GR quotient by the maximal compact HR that I called it before is actually a Kähler manifold. notice that SL2R belongs to both categories. Okay, so in a sense, starting with SL2R, there were two generalizations going in two directions. And so that split real groups, and another direction was the non-compact Hermitian groups of tube type. So the approach that I want to take to explain this, and was actually how this somehow initially appeared, is by means of the theory of Higgs bundles. So it's a complex algebraic geometric approach. And to explain that, I will now endow the surface, there was a smooth surface S, compact surface, with a complex structure. So this now, I will call it X, is a compact Riemann surface. Right? So now, okay, we are, as before, we have GR, a real form, and now, okay, this was the notation I was introducing before, I was not introducing before, which is HR is a maximal compact subgroup of GR. And once I have chosen this maximal compact subgroup, immediately after that, I have the composition of the Lie algebra of GR, they call this Gothic GR, as the sum of the Lie algebra of the maximal compact plus an orthogonal part, that orthogonal by means of the killing form. This is the Cartan decomposition. And this decomposition, this term satisfy this important relations that make them, you know, symmetric pairs, called symmetric pairs. In particular, one has the restriction of the adjoint representation. So you have the adjoint representation of GR in its Lie algebra. If you restrict it to HR, then you have two representations, one into the Lie algebra of HR, this, and another one, which is this one, is the isotropic representation, and we will complexify that representation. So H here is the complexification of HR, and this Gothic M is a complexification of MR, and I will allude to this representation as the isotropic representation. So strictly speaking, it's the complexification of the what one calls typically isotropic representation. Okay, I will try to remind you this notation because that we don't forget, right? So you have HR, and then you have the complexification of HR, which is H, and then the complexification of this part here, which is M. With these ingredients, now we can define what we call a GR Higgs bundle on the Riemann surface. And this is a pair consisting of a holomorphic principal H bundle over X. Remember, H was a complexification of the maximal compact of GR. And phi is a holomorphic section of the bundle. Here, this is a vector bundle associated with the isotropic representation via this representation, the isotropy here, and then tensored by the canonical line bundle of the Riemann surface. Okay, so this is what a Higgs bundle, GR Higgs bundle is on the Riemann surface. And just to give some examples to those not so familiar with this, if we consider, as I said, sorry, I should have called this not G, but G sub R. This is actually, as I said, this is a typo. As I said, sometimes our GR can be, in fact, any complex group can be thought as a real form. So I take in this particular case, GR to be SL and C. And then HR is SUN. And of course, the complexification of SUN is SL and C. And M is actually, MR is I times the Lie algebra of SUN. And M is SL and C. So because we are working with this classical group, we can think of Higgs bundles, SL and C Higgs bundles in particular, in terms of vector bundles. So this is a pair now where E is a rank in a holomorphic vector bundle. And because of the S here, the determinant of phi is fixed to be trivial, and the trace of phi is equal to 0. So these are the familiar objects that were introduced by Nigel Hitching. And as you know, there are notions of stability for these objects very similar to those for vector bundles. And the extra condition is that phi, the subbundle to which you check the stability condition, the slope condition, has to be invariant under the phi and so on. And you have polystable objects and so this, as I said, these were the original situation introduced by Hitching in his 1987 paper. Now, an example that is, again, I make a mistake here, it should be Gizabar. Gizabar is the symplectic group, the real symplectic group. It's interesting because this is both both a split real form and as well as Hermitian. I will come back to this group later on. So a maximal compact is UN, and so the complexification is GLNC, and the complexified isotropic representation, one checks this, decomposes in the direct sum of two irreducible representations. This is two symmetric product of Cn, and the same for the dual of Cn. And so in this vector bundle language, again, because the structure group of the bundle, remember the pair was an H bundle, is GLNC, we can think in terms of vector bundles. So an sp2nr Higgs bundle is a triple here, consisting of a rank n holomorphic vector bundle, V, and then a Higgs field has two pieces, right? Beta that goes from V dual to V tensor K, and gamma that goes from V to V dual tensor K. And this condition here makes that this must be symmetric. Yeah. So stability, just to give you a flavor of stability, here, is a more involved condition in the sense that it is not enough to check something for subbundles. Here, one has to consider the minimum. In general, one has to consider filtrations, but in the vector bundle context. But here, the minimum thing is two-step filtrations, and so there are notions of stability, polystability, and so on, right? Okay, so just to give you a flavor of these two examples, and then coming back to our general GR Higgs bundles, the thing is that, as I said, there are appropriate notions of stability and polystability, and the one can define the moduli space of polystable GR Higgs bundles, or semi-stable if you prefer. And this is what I will denote MGR or MXGR if I want to emphasize the Riemann surface. And there are several algebraic geometric constructions of this in the context of the original Higgs bundles. Nitin Tsure gave a construction using GIT, and then in more general setup of so Simpson, and in this generality here, Alexander Schmidt gave a GIT construction of these moduli spaces. Now, stability indeed appears naturally as a GIT condition, and how construct these spaces. But if you didn't know geometric invariant theory, you would actually find the stability condition arising from another point of view, which is the fact that one is looking for a solution to the Hitching equations. Now, in this context, because remember, this is an H bundle, right? So H was the complexification of a maximal compact. What one is looking for is a reduction of a structure group from H to HR. In the first example, that would be a Hermitian metric on the vector bundle, right? Or in the second example, that would be also a Hermitian metric on the vector bundle. So the general situation is a reduction from H to HR, this bundle, and that reduction that I will call H has to satisfy the Hitching equations. And here, FH is the curvature of the unique, the Chern connection that one has on this holomorphic bundle. Once you have the metric, the unique connection that is compatible with the reduction and the holomorphic structure. And then this here is a conjugation operation that involves both the fact that you have real form and you have a particular conjugation there, and the conjugation that gives you from 1-0 forms to 0-1 forms. Because remember, the Higgs field is a section of EM tensor with a canonical bundle. It's the canonical, right? And I mean, holomorphic, yeah. And so you are you have this operation, and this is the Hitchin equation. And the theorem says that a GR Higgs bundle has a solution to these equations if and only if is polystable. And this was proved by Hitching in his original paper for SL2C, and then by Simpson for complex groups, and with my collaborators Stephen Bratlow and Ignacy Mundet and Peter Cotton, we prove it in this generality for real groups. There is, in a sense, a proof by Simpson also in this situation by embedding the group in the complex one, but a direct proof of this and refining to stability, not just polystability, because in that process, going from GR to this complexification, you lose, it's just polystability. The only thing you can say is the one that we gave here. And so the important fact here is that is a non-abelian Hodge correspondence, that if you have a smooth surface that was our starting point for any complex structure, you can choose any complex structure on S, and you consider the Riemann surface, X, given by that complex structure, there is a homeomorphism between the character variety and the moduli space of Higgs bundles, GR Higgs bundles on the Riemann surface. And so the one way to see this is that if Phi is polystable, then you have a solution to the Hitchin equations, and then out of this solution you can construct a flat GR connection that is a representation of the fundamental group, which happens to be reductive, right? That's one direction. Now the other direction is you need another theorem. You need another existence theorem, and this is the theorem of existence of now for a flat GR bundle, the existence of a harmonic reduction. Now here we have a flat GR bundle, and we are looking for a reduction to HR. HR, remember, is also a maximal compact of GR, and so we ask that be harmonic, right? And this was proved. The existence of that, if the holonomial representation is reductive, was proved by Donaldson in a companion paper to that of Hitching for SL2C, and then in this generality by Corlett, right? So notice that if GR is actually compact, right? Of course, this is just the moduli space of bundles, and this is just the Narasimhan-Seshadri Ramanathan theorem, right? But in this non-compact situation, you do need this extra existence theorem, right, of existence of harmonic metrics, harmonic sections. Okay, so again, to a GR Higgs bundle, you can associate a topological invariant, and this is, of course, the topological invariant of the H bundle. And this is also an element in the H2 of X with values in the fundamental group of H. And this is isomorphic to the fundamental group of H, which is in turn isomorphic to the fundamental group of HR. So you notice that the invariant that one has in both situations, in the case of the representations and in Higgs bundles, is actually lives in the same place. And so if we now fix this topological invariant for the Higgs bundle, we can, as we did before for the character variety, consider the subvariety of Higgs bundles, GR Higgs bundles, with this fixed value of the invariant, right? And it should come as no surprise that the non-abelian Hodge correspondence restricts to giving a homeomorphism between the corresponding subvarieties with fixed invariant C. Okay. Please do not hesitate to ask me questions. You just have to tell me, because so that I can hear you well. All right. So this is the Hodge correspondence, a non-abelian Hodge correspondence, and this is our tool to study the problem that I was talking about, by converting the study of this problem in the character variety with fixed topological invariant, to a problem in the moduli space of Higgs bundles where I have all this, algebraic geometrical structure, analytic structure, and so on. And so the first situation where this higher Teichmüller spaces emerged was in the study of split real forms and what so-called Hitching components. So here GR is a split real form, and here's a definition. If you have the Cartan decomposition that you have by choosing a maximal compact, then the space MR contains a maximal abelian subalgebra of the full Lie algebra. If you want, the split real form is the less compact real form of a simple group, complex simple group. And so every complex semi-simple group has a split real form, right? And so some examples are for SLNR, SP2NR that we already saw. And for the orthogonal groups, we have SONN and SONN plus 1. And the same for the exceptional groups. You always have the split. So let me consider the case of the GR to be SLNR, the split real form of SLNC. And to exhibit these Hitching components, I want to tell you about the Hitching vibration, right? So to do that, one has that a basis for the invariant polynomials on SLNC, invariance under the joint action of the group SLNC, is, as you all know, provided by the coefficients of the characteristic polynomial of this trace-free matrix, right? You have the characteristic polynomial, and so these polynomials here are a basis for this algebra of invariant polynomials, and the degree of pi is given by I plus 1, and so we can define the Hitching map on the moduli space of SLNC Higgs bundles by evaluating. Remember that this was a vector bundle and phi was this twisted endomorphism by the canonical line bundle. And so we can evaluate phi in those polynomials, and we land in this direct sum of holomorphic sections of these various powers of the canonical bundle. Right. So this is the Hitching map, and the study of this vibration is a beautiful subject that is very relevant in many areas, in particular in the Langland's program, and both the original program and the geometric program. But the emphasis today is not on that, but the fact that one can construct a section of that map. So that is a map from this Hitching base to the moduli space here. This is what Hitching did. And that section, he actually showed that, in fact, lands into the moduli space of Higgs bundles for SLNR, that you can view it as inside of this. So in other words, that is corresponding to representations of the fundamental group in SLNR. And Hitching showed, in his paper in 92, 30 years ago, that this is a component, right? And that is called nowadays a Hitching component, is a Hitching component. For example, if you take GR to be SL to R, in this situation, the Hitching map really is just quadratic differentials, homomorphic sections of K squared. And so this Hitching component coincides with the Teichmüller space identified as with the quadratic differentials. Right? Now, so Hitching gave in his paper actually a general construction for any split real form, and not just SLNR, but any real form. And this component is unique if GR is a split form of adjoint type, so we quotient by the center. So you see, when we saw before SL to R, remember there were 2 to the 2G connected components. And I said that all of those can be identified with Teichmüller space, and you may be surprised because you think, there's only one component, the Teichmüller. And the fact is that with in the context of Teichmüller theory, you consider PSL to R, which is just the quotient of SL to R by the center. And so all these 2 to the 2G connected components in SL2R, when you map to PSL2R, they all collapse to give you just one component, right? So now, so something that happens is that this Hitching component can be characterized by the following fact, that every representation in the character in this component can be deformed to a representation that factors through a representation in SL2R, and then this here, this map from SL2R to GR is the principal representation that every split real group has. Principal representation. There is always this principal representation from SL2R to the split form, and so the Hitching component is characterized by this. And so here's in this business of Hitching higher Teichmüller spaces, another fundamental piece in the theory. One is the Higgs bundles, but then another is the work of François Laborie, who introduced the concept of Anasof representation. I'll say something about that later on. But so these Anasof representations have many interesting geometric and dynamical properties. In particular, they are discrete and faithful. And what Laborie showed is that the Hitching component consists entirely of Anasof representations, and hence they are discrete and faithful. This is the property we were after. Okay, now, let me go to the other second family of groups. These are the groups of Hermitian type, and this simply means that the symmetric space here admits a complex structure compatible with the Riemann structure. And because of invariance, homogeneity, this is actually a Kähler manifold. And for the classical groups, we have, for SL and C, we have SUPQ. We have here the symplectic group SP2NR, the split real form of SP2NC. And then for the orthogonal groups, you have this non-compact dual of SO2N. And then here, I mean, I put this because I want to consider a connected component. But later on, we will actually, in dealing with orthogonal groups, I consider non-compact, non-connected groups. And then there are two exceptional real forms, one of E6 and another of E7. And this is all for, groups that are, these are examples of groups up to finite covering that are of Hermitian type. And in this situation, then when GR is simple, the torsion-free part of the fundamental group is isomorphic to Z. So we're in a situation similar to SL2R. And then the topological invariant here is again an integer. And this is called the Toledo invariant. In the SL2R, the Euler number is called the Toledo number or Toledo invariant. And so here is a generalization of the Milnor inequality in this context, and that the Toledo invariant satisfies that it must be is bounded by the rank of the symmetric space times the genus -1. This was proved for the classical groups. There are a lot of work for the classical groups in terms of representations by Turayev for the symplectic group, but Domich and Toledo for the classical groups. And in the language of Higgs bundles, this was proved with my collaborators Peter Gotten and Steve Bradlow and Peter Gotten. And a general proof we know using classification, so including the exceptional groups, this is given by Berger, Yotzi, and Winhardt in terms of representations, and using Higgs bundles in my work with Picard and Rubio. So what we want to study is the case of maximal Toledo invariant. There is where we will find our candidates for higher Teichmüller spaces, and like we did in the case of SL2R. And so here maximal means that the Toledo invariant in absolute value equals the rank of the symmetric space times the genus -1. And let me actually, to give you a flavor of what happens, to consider the particular case of SP2NR. SP2NR, as I said, is both a split and Hermitian, right? So, but recall that an SP2NR Higgs bundle of the Riemann surface, as I explained before, was defined as a triple consisting of a vector bundle of rank n, holomorphic vector bundle, V. And then we have this symmetric homomorphisms from V dual to V tensor K and from V to V dual tensor K. That are the objects. So the Toledo invariant coincides actually with the first chain class of the bundle V, is the degree of the vector bundle V. And it's interesting that the proof of the Milnor-Wood inequality that I mentioned before, yeah, there's a general, this thing here, you see involves the rank of the symmetric space and genus -1. Actually, the Higgs bundle point of view is somehow more powerful than the representation point of view, because it gives you a refined inequality, in the sense that, in fact, you obtain a finer inequality for the Toledo invariant, involving, in this particular case, the rank of beta. Yeah, so this is an n by n square matrix, and the same rank of gamma. Of course, the maximal value of the rank is n, and that's why we get the Milnor-Wood inequality. But we have this more refined inequality. And this more refined inequality is the key to deduce the following: that if we assume that D is maximal, that, remember, that was the interesting case, and say positive, something similar happens for negative, then by just inspecting this refined Milnor-Wood inequality, you deduce that gamma, this gamma here, has to be an isomorphism of vector bundles. Right? I leave this as an exercise for you. It's very easy. It says, you know, the just because of the values of this, and you cannot be torsion in the quotient, and so so we have an isomorphism. Gamma is an isomorphism, and you would like to say the gamma is an isomorphism, and because symmetric, you would like to say that it's like an orthogonal structure on V, except that we have a twisting by K. You can actually talk about twisted orthogonal structures, but instead, something you can do is actually choose a square root of the canonical line bundle, any square root, 2 to the 2g, choose one, and then we define a subsidiary vector bundle, which is the tensor product of V dual tensor L, and then we can recast the Higgs field beta, right? So sorry, before I say that, then Q, so gamma in terms of W becomes a true orthogonal structure on this bundle W. So you do have the W equipped with Q that morally is really gamma, is an orthogonal, is an ONC holomorphic bundle, right? And now you can express beta in terms of this Q using the isomorphism that we have to define out of beta and this Q, this gamma, in this way, an endomorphism from, so beta now is has avatar is a endomorph, well, it's a map from W to W tensor K square. So this is, you know, you think this is like a Higgs bundle now, but it's not twisted by K, so it's twisted by K square. So if you think about these ingredients and the definition that I gave of GLNR, excuse me, of GR Higgs bundle for K, you can do that for any twisting line bundle, and so in particular K square. So you realize that putting these things together, the object that you get, yeah, W together with Q and this theta, is a K squared twisted GLNR Higgs bundle. So if you put this together, what we prove is that there is an isomorphism of complex algebraic varieties between the maximal Toledo invariant, the M max for the symplectic group, and another moduli space for another group, GLNR, but now twisted by K square, not by K. So this isomorphism here of algebraic, complex algebraic varieties exhibits already something that is one of the things that we wanted, is that here we have fixed the Toledo invariant to be maximal, yeah, this value, d equals n times g minus 1. And all of a sudden, we uncover the existence of other invariants that somehow are hidden at the beginning. And these are the Stiefel-Whitney classes of the orthogonal bundle W, right? So this is, there is, you see this phenomenon of having components that are not distinguished by the primary invariant, which in this case is the Toledo, maximal Toledo. Now, how does this generalize? So the group SP2NR happens to be what is called a Hermitian symmetric space of tube type. We should not be scared by this. Let me explain what this is. Actually, think of the Poincaré disk, right, which you obtain for SL2R. The Poincaré disk is biholomorphic to the upper half plane, and this is established by the Cayley map that we all study in school, and when we study complex variable, one complex variable functions, and so on. And so this tube type Hermitian symmetric spaces are those for which, like the case of the Poincaré disk, there is a upper half plane model, sort of, right? So every Hermitian symmetric space can be realized as a bounded symmetric domain, right? In a complex vector space, as Kartan and Harishchandra, right? Realization of this as a bounded symmetric domain, and as a bounded symmetric domain, there is a boundary, a part of the boundary of the topological boundary, sometimes the whole thing, like in the case of the disk, is the circle, which is called the Shilov boundary. It's characterized by several properties, but one is that is the component of the boundary, the only component of the boundary which is invariant under the action of the, higher dimensional orbit that is invariant under the action of GR. But another characterization is the following: the Shilov boundary is actually, in general, a homogeneous, is a homogeneous, compact homogeneous space. And now, the definition of tube type is that when that is actually itself a symmetric space, a compact symmetric space, right? And when that happens, then here is what we call Cayley correspondence that was proved. I'll talk about the proof. So if you have a Hermitian symmetric space of tube type, which means that this is actually there is a subgroup of HR, which is H prime R, for which this is compact symmetric space. Remember that symmetric spaces come in pairs. When you have a compact symmetric space, there is the non-compact dual. And I denote the non-compact dual like this. Yeah? Well, the theorem says that the maximal Toledo invariant Higgs bundles with, for GR, this moduli space is isomorphic to the moduli space of K squared twisted Higgs bundles for this group. Yeah, this group. You see, in the case of, let me say, in the case that we just saw of the symplectic group, this maximal compact, remember, for SP2NR was UN, right? And this happens to be ON, right? And so this symmetric space, right, is a compact symmetric space, UN, quotient ON, and the non-compact dual is GLNR mod ON. That's why the group that appeared there was GLNR. So this is the general theorem. And so this was proof in a one-by-one situation for the classical groups in several papers with my collaborators, Steve Bradley, Peter Gotten, and Ignacio Mundet for different cases. And then the general proof with no using classification theorem was given by with Bicard and Rubio. Now, as in the case of the Hitching components, the theory of Anasof representations introduced by Labourie in collaboration with Burger, Yossi, and Winhard they proved that this maximal Toledo consists entirely of Anasof and then are discrete and faithful representations. And something I didn't mention before for the case of the Hitching component, but it's also true for the Hitching component, which is a fact that the Teichmüller space, the usual classical Teichmüller space enjoys, is the fact that the mapping class group of S acts properly on these components. This was proved by Anna Winhardt. So these are all common features of the Hitching components. And so the question that arises, around these years and so on, after the case of split and Hermitian had been completely solved, was whether there are other groups besides these two classes of groups for which this phenomenon happened, for which there are these special components, right? These higher Teichmüller components. For a while, it was believed that these were the only classes of groups, but then there was another family of groups that appeared and having these special components, and these were the SOPQ. I mean, SOPQ, of course, can be a split and can be Hermitian, but I'm talking about SOPQ for P and Q that is neither a split nor Hermitian. And so it turns out that if you take SOPQ, so here is an instance of a group that is non-connected. You can do this for the connected component, but let's do for the whole thing. And so the if you fix the right topological invariant, then you can prove that there is always a component that has that fixed topological invariant, and which has this feature that every element in that moduli space with this fixed natural topological invariant so there is a connected component. I mean, when you fix the topological invariant, I'm saying there is a connected component in particular, right? That has a property that every representation there, or every Higgs bundle, can be deformed to one in which the Higgs field actually is zero, and therefore is really a representation. So when the Higgs field is zero, that is a representation to the maximal compact of SOPQ. But the interesting thing is that we proved that even with fixed topological invariant, there are other non-empty components that are not distinguished by this. And the way that we detected this is by some kind of Cayley correspondence as before. So we proved the existence of some Cayley correspondence, and we identified these components, right, as actually this other moduli space for P and Q. It was this moduli space for another group with twisted by KP, and then this holomorphic differentials here, right? Yeah. So this. You see, the first author in this paper is my former student, Marta Aparicio, to whom I gave this as a thesis problem, thinking that this was a situation where, besides the Hermitian situation when P is 2 or something, this was going to be, I thought, a situation where the topological invariant is going to characterize the components. And so she was using the methods of Hitching, as we have done in all these studies, the Morse theory applied to this, given by the Hitching function, the L2 norm of the Higgs field, to study critical subvarieties and minima, and that's how you study this. And so she found
minutes.
See, now it's a flat cut.
Oh, outside?
No, sir. I think it's from there. Yeah, see, I think it's actually moves. The volume is not.
He left, sir.
And
Yeah, his connection is lost.
Yeah.
it's straight, probably he will reach out.
We internet down at that time. That's why our connection. Internet issues, sometimes Zoom automatically close. Okay.
Some messages there.
Yeah, good. Surat mode. Yeah, about to finish.
Do you know Oscar's WhatsApp number? Oh,
We have this.
but if the internet is down, then.
Next speaker can speak and whatever the connection. Yeah.
You don't have any. You don't have any hospital? Oh, good, that's a very good news. Then we can be. Then we can be.
Right.
Hello. Yeah, so, yeah, there seems to be no connection.
It's going to be a lecture.
Okay. Okay. Try to come back.
Hello? Yes, share screen. Yeah, desktop. Here.
Hello. So do you want to share your screen again?
Yes, let me try to do that. I don't know what is just stop. No, wait a minute. Okay, sorry, 1 second. I launch meeting. Yeah, sorry. No. Yes, I want to share my screen. Sorry. Do you see me now?
Yeah, we can see the slides and you
Okay. I think, sorry about that. I don't know. We have a cyber attack in my institution, but I don't know what is happening. I'm at home. I don't think I have a cyber attack. Something happened. Sorry about that. So I think I was telling you about SOPQ, right? And I was saying that we found this special components for SOPQ, and I will discuss about why those components also have this property of being entirely discrete and faithful. And this has to do with some work done by Guichard, Labourie, Winhard, based on previous work of Guichard and Winhard on something called positivity. And this was, from their point of view, this was also evidence that something was happening for SOPQ. That was what gave us also encouragement to revisit the previous work of my former student, Marta Paricio, in her thesis, and wrote that paper. So the main goal of the rest of the talk, hopefully uninterrupted, I hope, is that to actually give a full classification of the Lie groups, all the simple Lie groups for which this phenomenon happen, right? And in fact, not just give a classification of these groups, but actually give a general Higgs bundle parameterization of those components, right? Like similar to what we have done to the Hitching component and to the maximal Toledo and so on, to the SOPQ. And so this is joint work with Steve Bratlow and Brian Collier, Peter Gotten, and Andrea Oliveira. You can find the archive, has been there since January of 2021. And so the key to find this classification from the point of view of Higgs bundles is given by the theory of SL2 triples, and in particular, certain nilpotent elements and corresponding SL2 triples. So let me explain this. I don't know how I'm doing time-wise. You let me know if I'm going beyond my rights. And
you have actually 9 more minutes.
Okay, very good. I'll try to do this. So we start with a complex simple Lie algebra, simple complex Lie algebra G. And so remember that you say that an element in the Lie algebra is nilpotent if the action by the adjoint in the Lie algebra is a nilpotent endomorphism. And so we have the nilpotent cont inside the Lie algebra, and the group acts on the nilpotent call by conjugation. And there is one important orbit, which is the so-called principal orbit, and that is the unique open and dense orbit. And there is the important result of Jacobson-Morozov correspondence that tells you that you can, given a nilpotent element, every nilpotent element, not just principal, you can complete it to an SL2 triple, right, by elements F, H, and E, so that they satisfy the relations of the SL2 C algebra, right? And that there is a bijection between the orbits in the nilpotent cone and the orbits of these SL2s that are produced by the SL2 triple. The SL2 triple generates an SL2C, a Lie algebra inside G, and so there is a correspondence between these two equivalence classes. Okay, so if you give me a non-zero nilpotent element, E, let's say, consider you complete it to an SL2 triple, right? FHE, and then just consider the SL2C Lie algebra generated by it. Okay, so here is what happens. you have two different decompositions of the Lie algebra G. And one decomposition is as an SL2C module. You know, SL2C is acting on G, right? And so G decomposes as an SL2C module in direct sum of WJs, right? Where you have here the WJ has, you know, direct sum of copies of the reducible representation of SL2C. So you have this as an SL2C module. But then you have another decomposition, which is by using the element H in the triple and take the eigenvalues, eigenspaces by the action of H, by the adjoint action of H. And this gives you this decomposition of the Lie algebra in terms of G sub J's, two decompositions as eigenspaces as SL2C modules, eigenspaces for this action of this element H. Now you can combine these two decompositions, right? And somehow you can write the Lie algebra as a double direct sum of these highest weight subspaces Vj, yeah, which are defined like this. And in terms of operating, you know, adjoint of F as many times as necessary. So you have this decomposition. And so once you have that decomposition, you can define an involution of G as a vector space. And this involution as a vector space is defined like this. You can believe me, this defines an involution in the vector space, but then something special happens sometimes, right? And this is what gives rise to the notion of magical, in lack of another name, we call this magical, SL2 nilpotent, magical, excuse me, nilpotent or SL2, whatever, when this vector space involution is actually a Lie algebra involution. That happens sometimes. And so when that happens, then you can decompose the Lie algebra G in H plus M, the plus and minus one eigenspaces. And then this is essentially, by Cartan, you can find this is associated to a real form. There is a canonical real form attached to this. So once you have one of these nilpotent magical things, you do have like a real form appearing in the Lie algebra, GR of G. Okay, so we gave a classification of the groups, the real groups that can appear as from a magical nilpotent. And it turns out that the list is the following. You have the split real groups, no surprise, Hermitian of tube type. Then you have locally isomorphic to SOPQ. And then the list is completed by exceptional groups, some real forms of E6, E7, E8, and F4 that are characterized by the property that the symmetric spaces that they define by quotienting by the maximal compact is quaternion Kähler manifold, right? So this is the whole list. And so this list coincides with this classification of groups admitting a positive structure given by Guichard and Michard, that I will come to this later, right? And so what do you do? So the magical triple, a magical triple, when you have one, actually gives you more information. There is more structure in the Lie algebra that you can extract from it. You can extract this real form, right? But actually you can extract, this is quite technical, I don't have time, and you can extract some integers, M1, a distinguished one MC and Mn, and actually a real form, yeah, of G0. Remember, in this decomposition of G in terms of GIs as eigenspaces for the action of H, there is this G0, and then you get also real form of the G0. And once you have that, then, so what we prove is that if E is a nilpotent, magical nilpotent with corresponding canonical real form GR, and if the group GR is a Lie group with Lie algebra GR, then there exists a union of connected components in the moduli space determined, actually is basically determined by the orbit of E, not by itself, but the orbit of E, that the Higgs bundles that one has there have nowhere vanishing phi, right? So they cannot be deformed to representations of the fundamental group in a maximal compact HR. That's one thing. And also that this union of connected components can be parameterized, can be identified with another moduli space, which is now a moduli space of twisted Higgs bundles, where the twisting is given by this MC plus 1, by K to that power, for the group, this real group corresponding to this Lie algebra, and then a bunch of differentials, right, of holomorphic differentials. So not only you prove existence, but actually that it can be identified with this other moduli space, from which you can actually extract new invariants and so on. So this parameterization is actually given by starting with this thing here, right, and this thing here, and defining explicitly a map to the moduli space of GR Higgs bundles, which we call the Cayley map. And we prove that this map is an isomorphism onto its image, which is open and closed in MGR, and hence it defines topological components. We call those Cayley components, because this map is defined by means of a Cayley correspondence, a Cayley map in the context of triples, of SL2 triples. So this map recovers the Cayley correspondence for Hermitian groups of tube type, as we saw before, and also the one for SOPQ, and somehow more surprisingly, it recovers also the construction of the Hitching components in the split case. You see, I have never thought of the Hitching section really as a Cayley map. And it turns out that the Hitching section is really an example of this, right? And that is obtained precisely out of the principal nilpotent. The principal nilpotent that always exists happens to be magical. And so that magical nilpotent, principal nilpotent, or the principal SL2 triple gives you exactly the Hitching map. So you see, in this, if you see this correspondence, you see that there are like two pure situations. One is like the Hitching map where you only have this kind of thing and nothing here. And then there is the Hermitian situation where you don't have these holomorphic differentials, you have just this here. And then you saw SOPQ that has a mixed combination of both. And then the exceptional forms also are a combination of these two situations. Now, so let me just finish by saying something about why are these have the right to be called higher Teichmüller spaces, right? And this relates to this notion of positivity that was introduced by Guichard and Winhardt, and is a notion that involves a choice of a parabolic subgroup of GR, right, of our real group. And this positive structure is something, yeah, that is an elaborate thing, but it's something that allows you to define in the Flack variety some notion of positive triple. I have no time to get into that. But this is an important notion that actually generalizes a previous notion that had been introduced by Lustig, something called total positivity in the split real forms. And also in the Hermitian case, there had been some notions of positivity using the Maslov index in the Hermitian groups case. So this notion that Guichard and Winhardt introduced generalizes all of them, right? And so the thing is that if you take the GR to be SL2R and you take the usual parabolic, right, then this is the circle. And so, so in this case, is the notion of positive triple is just to be pairwise distinct points. And so here's how you define a P positive when you say that a representation is positive with respect to this notion of positivity. And there is something called, if you have a representation of the fundamental group in GR, there is something that induces a map from the boundary at infinity of the fundamental group. This is just a circle. You think of the Poincaré disk, and this is a circle, into this generalized Flack variety. And you say that it's positive if it sends positive triples in the circle to positive triples in this flag variety that you know what it means because of this positivity structure. Now, the thing is that in recent work, Guichard, Labourie, and Winhard proved, so this is in the archive in June 2021, that if you have a group GR with such a positive structure, then actually the representation is positive, then it's automatically Anasof, and therefore discrete and faithful. And the set of positive representations is open in the character variety. This was known already, actually. But the key point is about closeness. And they wanted to prove that the set of positive representations was closed in the full character variety. They didn't quite prove that. They proved that it was closed in the sub-variety of this, of representations that do not factor through a parabolic subgroup. But that was enough for us to conclude the following, because we, in our paper, had proof that these components that we had, had that property. So we proved that, in fact, there was some subset of representations that are positive. Therefore, by openness, there is an open. And then we prove that our representations there do not factor through a parabolic by using Higgs bundle techniques. And therefore, the conclusion is that the Cayley components consist entirely of positive representations and therefore are just higher tabular spaces. You see, they wanted to prove that this was closed in the full character variety. This was something that actually Bader and Pozzetti actually proved. It was known for the split groups, it was known for the Hermitian groups, and Bader and Pozzetti proved that it was true actually for the OPQ groups by using something called color lemmas. And now it's believed that actually is also true for the true for the other exceptional groups. So therefore, the conclusion is that our components, Cayley components that we obtained by this construction, by these magical triples, are all the higher tabular spaces that you can see in this context. And I think I should stop here. Thank you.
Thank you. Is there any question? So if there is no more question, let's thank the speaker again.
Thank you. Stay well.
So the last talk of today's is cancelled. So we are going to stop. Yeah.